So, limit cycle. Now, we can view this model. This is a stock and flow model with two stocks of model state. So we can represent the model state by two variables. We can also represent this in agent-based form. So I'd like to take a look at an implementation of this as an agent-based model. And this is called predator-prey grass, and it's on the canvas if you want to follow along, but this won't be an exercise today. So if we look at the structure of this agent-based model, all models in any logic have a main agent. We also have what is called a patch, and then a predator and a prey animal as agents. So there's three key agent types, and then the main agent in which they live. In main, there's a population of patches, and this is a way of representing the environment as patches or grid squares or cells. The patch has some structure to it. So inside every patch, it's represented by a square. And it has a color, which is determined by the state chart state. And then there's a population of prey animals that's initially empty. And also of predator animals, which is as well initially empty. And we have a state chart representing the state of that patch in terms of the vegetation that's growing there. So there could be no grass. We have a flag where we can turn off grass, and the prey animals don't need to eat, and there's no representation of that. Or it may have lush vegetation, or it may be barren. The grass may be eaten, as represented by this transition. And after a certain time, it'll regrow, as represented by this one. So let's now look at the prey animal. The prey animal starts alive and may die. While it's alive, there's a couple, these are called internal transitions, and these will go off every so often, according to their rule, while the agent remains in the state that they're inside of. So we have one called daily energy burn, which represents the daily activity of the animal. So the animal will burn energy. This is the prey animal. So if grass is not enabled, we don't worry about how much energy they burn. And then it'll try to eat. So if the patch is lush with grass, it will eat the grass and gain energy from doing so. Otherwise, it'll move to a nearby patch in search of grass randomly. So there's an energy variable, and when that gets below zero, then it's a starvation death for the animal. And since these are prey animals, they may also be eaten by the predators, which is represented by this transition here. Now, if we look at the predator, it has a similar state chart. It also has an energy variable, but its behavior is slightly different. So the daily energy burn, predators always burn energy. and they will try to eat. If there is a prey animal at the same location, they will kill it and eat it. If there's no prey in the current location, they'll randomly go to an adjacent patch in search of prey. Predators, nothing eats the predators. We only have one level to our food web in this model, but they can starve to death if they can't find enough prey. And the other internal transition in the alive state that I didn't discuss yet is reproduction. So and this works in the same mechanic for the predator and the prey, if they have enough energy, then they will add a new predator animal, and they'll suffer a loss of energy from the reproductive act. So those are the key agents. I want to go back to main and we'll look at a couple other things. So we had mentioned observer processes in agent-based models, or any model, in fact. And I've set up a basic example of that in this model. So we have some statistics, and this is an event object in any logic. So we can put code in this code block, and we can tell it to go off at a certain time in the model execution. So this is by a timeout, and it's cyclic, so it happens over and over again. So the first time it happens is at 0 days model time, and then every 1 day interval after that. Because it's a timeout, it's exactly 1 day. We have other options here, and it could be a rate or a condition, but we won't worry about that right now. Those behave similarly to the rate and condition transitions on a state chart. So what this event does is it computes some statistics, just the count of the prey, the count of the predators, and the count of the grass that is lush in the model. And then it adds them to these data sets. So a data set is a structure that contains data, and you want to use that when you want to preserve data till the end of the model run or display it in a graph while the model's running. So these data sets are referred to by the graphs in main. So there's a time series graph, and there's a few state space graphs. And the final thing I want to draw your attention to in this model is we've got a basic file output mechanism that'll output it to a comma separated value file. So that's what this represents, the text output file. And then we have a function called write state, which will write the amount of grass, prey, and predators out to that text file for analysis in another environment. The setup output simply initializes the file and writes in the headers for the columns. So I'd like to move on to running this model, and keep in mind that we just saw the stock and flow version of this. And I'm going to start with the no grass scenario. So in the stock and flow version, we didn't have any representation of food. The prey animals just reproduced at a certain rate and could be eaten by the predators. So this is analogous to that in that sense. So I'm going to run this, and we'll see the model running. And I'm going to speed it up a bit. Actually, maybe what I'll do is I'll pause it and we can discuss rather than jumping in. What do you think is going to happen with this model as we run it? What do you expect to see based on what we saw in the system dynamics or stock and flow version? Any thoughts?
A limit cycle.
Good. So we can expect the limit cycle, or we should, or could. What do you see here? So this is, these three graphs represent the state space. And there's three of them because we have three variables and they're showing different views. So this is grass and predators. Note, we don't have grass turned on, so it's just a straight line. This one is grass and prey, and again, it's just a straight line because we're not implementing grass in this scenario. So this is where we can expect to see the limit cycle between prey and predators. But what do you see that's different about that graph that we've just in the first few steps of the model? Yes.
Not smooth.
It's not smooth. And that's Eric.
Yes.
Thank you.
Because it's rather than being a mathematical equation, it's based on specific time steps. Or well, not time steps, but like.
So that's a good hypothesis, but we're actually running this model in continuous time. But we're collecting the data at exactly 1 day intervals. But the reason it's jagged is actually because the agent-based model features something that the system dynamics or stock and flow model does not. And does anyone have an idea?
Probably the number of predators at each time momentarily probably plateaus and then moves on again as the number increases, or the prey number also goes down.
Okay, I think you're going in the right direction there. Yes.
Would it be that we're now taking into account location of the predator and the prey compared to the stock and flow? We just assumed that prey, based off the statistic, would be able to find it.
That's another good hypothesis. And we are doing that, right? This is a spatially explicit model because the animals exist in this grid. And it may be that a predator is at a place where there is no prey and it doesn't get to eat. It may be, well, we'll leave that till the next step, but yes.
There's also two other things. One, the last model assumed that every predator had an equal opportunity of getting a prey based on how much prey is around. Where in this, the prey could be distributed to one side of the graph and the predators another, or just slightly different things like that, which could cause it to be jagged like that.
Yeah, and that ties into what the others said. That was Johnny and Elliot.
Yeah.
And also it's a much smaller scale. So
yes,
errors in that can be more evident.
Those are all collectively, those are all good observations about the model. If we look at this model, our number of predators, what can we say about that? And our number of prey, what can we say about the type of that? To think about it in a computer science perspective, what type is that number? Is it yeah, Jihan? Integer. Yeah. Int. Correct. So it can be 1, it can be 2, but it can't be 2.5067. And that is a key difference the system dynamics model has continuous values for its stocks. So while it can be a good approximation for a system like this, in reality, we can't have 2.5 animals. Or
Sort
But-
of the system of infinite size to a degree.
yes, and that's a way to look at it, right? You can imagine that the system is larger and that these numbers, rather than an exact count of the animals, represent a probability that you have this fraction of animals in the capacity of the system, right? But in this model, we have a limited space, and we have an exact number of prey animals as an integer and an exact number of predators as an integer. So these jumps here, like from here to here, it looks like it's going from 43 to 45 on the predator's axis in a step of 1 day. But it's not going to move smoothly because it can't be 43.5, right? It has to jump from one integer value to another integer value.
It's also probably worth noting it is stochastic.
Yes, so thanks, Professor. The other thing, the place I was originally going with that, but there were great comments, so thank you all who commented. The agent-based model is stochastic, which means it has randomness in it. And we didn't really emphasize that in the when we went through the agents. But one of the places where randomness is introduced is when an animal goes in search of food, it goes to a random nearby patch of grass to look for food, whether that's predator or prey animal. And some of the transitions were rates, which also introduce randomness or stochastics.
Yeah, we might note that the word stochastic is referring to randomness over time. So you might have randomness about other things, like randomness in the initial state or what have you, where things are distributed. But to say it's stochastic means further that there's kind of coin flipping going on as the model runs. Over time, there's chance events.
Yeah, thank you. So let's run this and see what happens over a period of time. So you can see the graph evolving over time here, and it's jagged, representing the fact that it's stochastic. The gray is the prey and the red is the predators. And we can see here the limit cycle beginning to form. But again, it's jagged. So if we look at the time series, our predators. Oh, what just happened? How many predators do we have left? It may not be obvious sitting in the audience, but there's a display up here. It says there's 132 prey, 0 predators. So they've gone extinct. And that's something that can't really happen in the stock and flow model, because we could have a fraction of a predator and we could interpret that as a probability or a fraction of the total capacity of the system. But here, when we get an exact 0, there are none left. So let's let this go again. And look at the prey in absence of predators eating them are growing exponentially. So what I want to emphasize here is because of the integer values for the counts of animals, and because of the stochastics, it's possible for something to go extinct in this model, whereas in the stock and flow model, it's not generally going to happen because we can have even a tiny fraction of an animal is considered non-zero. So the next one I want to run is a no predators scenario. So this will have grass. You can see the grass starts green or lush, and then we have prey animals around the map, and they're eating the grass. No predators in this scenario. What do you think is going to happen? Jihan? That's a great hypothesis. Johnny?
Yeah, so, since the prey does not feed, we don't know whether the prey is able to also feed on the grass. But if they are not able to feed on the grass is going to continue to increase while the prey population will decrease. Until there is any, yeah.
So, okay, so the prey can eat the grass, and they do need to eat grass in this scenario. So I'll clarify that.
Okay, so it means that they are going to eat the grass until the grass will finish. But if you have a predator population, then it would also be feeding on the prey until the prey builds an equilibrium.
All right. Hey, Sheena, you had something to say?
I was just wondering, sorry if I missed it, sorry, but does the grass regenerate at all, or is that not a factor?
The grass does regenerate, and I went over that quickly when we were looking at the different agents, but after a specified, parameter amount of time, the grass will grow back. So those are some good ideas. Let's run this. Is it running? I said run. Let's use this control. So let's speed it up a little bit. So we can focus on the time series. You can see the green is the grass, and that's going down as the prey multiply.
You might note that emphasize that the brown is denuded grass.
Yeah, the brown is eaten grass, and the green is lush grass. So we've got tons of prey animals now. What do we see on this time series? They're reaching an equilibrium. So Jihan had suggested that it would go down again. But it's actually, it is going up and down a little bit if we look very closely because of the stochastics in the model. But it's actually coming to an equilibrium where there's enough grass to feed that many prey animals. And if we run this. If we run this out. They kind of stay in an equilibrium. There's a bit of variation, again, due to stochastics, but they don't form a feedback with cycles the way the predator and the prey animal together in the no grass scenario or would. Why do you think that is? Any thoughts?
I think the grass, the amount of grass available is just enough to sustain the prey. It's not too much for the prey to increase that much, but just to keep it at that base. So the prey may not increase that much, and they may not die that much because there is just enough of the grass to eat.
At the back there?
Is it because the grass population is independent of any other variable?
Yes. And your name, please, again?
Also,
Abdul. Thank you. A couple others had thoughts, like Sheena.
Is it because there's no like, delay associated with the grasses? No delay in that, so then there's no like oscillations of up and down, if that makes sense.
Yes, I think I get what you're saying. Jihan, you also wanted to comment?
I was gonna say like the same thing, in the prey there, hopefully so that they put to the grass. It can influence the top. Great.
Yeah. And I think that's a key observation. The grass, there is a delay on the grass growing back, but it's a fixed delay specified by a constant number. It doesn't depend on the number of prey animals or have any effect there. But the prey, the ability of the prey to live depends on the grass being there, but there's no two-way relationship there as there are between the predators and prey.
Yeah, the presence of this delay, some of you may recall from the system dynamics stock flow discussion, when we have a delay introduced into a feedback, you get oscillation. And this reflects that even though the model's at a much more fine-grained level, in terms of the total populations plotted, you get these induced cycles. I think there was maybe a hand.
Was there another question?
Emilio.
Did I miss?
Emilio, did you have your hand up?
Okay, thank you. All right. So let's now run the full model, which I've called the baseline scenario. So grass is enabled. There are prey and predator animals. So let's take a minute to think about what do we expect to see here now with all three types of life involved in the system. Yeah.
Like maybe like the different cycles that we have just with no grass, but then there'll be a limit to how much prey there can be, like before, if we added more prey, the chain, or added more predators, but now it's. That's one.
Okay, that's a good idea. Anyone else have any suggestions? Eric?
I think the presence of grass will cause the prey to be more spread out, so the predators will have more opportunities to find prey, thus making the model have a little bit higher chance of not having the predators die. So it creates a proper cycle that more represents.
Okay, that's a good thought. Anyone else? Sheena?
Would grass go up at the same time as predators going up because the decrease in prey? So it's like grass and predators almost have similar waves.
That's an interesting thought. We'll see what happens. So
Maximum minimum number of the prey and predator affected by the amount of grass. It means that the maximum and minimum can be changed over time. The different equilibrium point for the maximum number of predator and prey to change over time, because the amount of grass can affect the maximum number of.
okay, so that was Mehdi. Thank you. Johnny?
Yeah, so I think that initially the grass, the amount of grass and then the prey may be reducing while the predator will be increasing. At the initial aspect of the model, until there's equilibrium where there is prey and grass and then predator in equilibrium.
So you expect it to reach a fixed equilibrium like we saw in the previous scenario, like where they're basically straight lines in parallel? Or
At some point, and then the prey will go down, grass will go down, and then the predator will go down and then plateau.
okay. So those are some thoughts. Thank you. Now let's run it and see what happens. We'll speed it up a little bit. So we can see prey are growing. Predators are growing, but more slowly. Grass is being reduced. And now it looks like the prey have peaked. And predators are growing. We'll just speed this up a little bit more, and then we'll complete a cycle, and then we'll pause it. I'll slow down the speed again so I don't run it really fast when we get back to running. So if we zoom in a bit on this time series, so how does this align with the different hypotheses that we had come up with prior to letting this run? Does anyone want to comment, Pius?
So the grass is related to how many prey there are to eat the grass. And then also it's related to predators, as when there's more predators, there's less prey, and so there's more grass.
Yes.
Yes.
Any other thoughts?
Which is the predator and which is the prey?
So I've got that off the screen. I apologize. Predators are red, prey is gray, and grass is green. Yes.
Predator. Yeah. Predators will lag behind the prey, and the grass will correlate with however many prey, but inverse, because they're trying to get to that equilibrium that they were without the predators, but the predators will in turn increase, in turn decreasing prey and increasing.
Yeah, that's a good comment. So anyone else have any other thoughts on that, Johnny?
Yeah, so you see that, so my initial thought had been that the grass and the prey may be reducing, but that's not what we saw. The prey and the grass, the growth is in the opposite direction at the initial, until the prey gets to the peak.
Yeah.
We get to the peak where there is no significantly reduced grass, and then the prey will begin to go down while the grass would begin to increase. At that same time, the predator slowly rises, the population slowly rises until it also gets to the peak where the prey population is very low or at equilibrium with the predator, and then it begins to go down.
All right. So we see, as was observed by you folks, we see that the grass is sort of the inverse of the prey. And the predators lag the prey like they did in the other model. So did you have a thought, Sheena?
I wonder, does like the peak in grass also directly correlate with the crossover between predator and prey, or is that just what happens?
Well, we can line it up here. Oh, so you mean like
Like, or
this intersection?
but
It's difficult to say for certain because of the stochastics, but I'd be inclined to say it probably is not exact. What are your thoughts, Professor?
So Akshina was asking if that intersection between the prey and the predators was correlated with the peak of the grass?
That's correct.
or like I guess we started the decline in grass, but that's also because just the prey's going up.
Right. So the grass, if you think about it, the inflow and outflow from the grass. The grass grows naturally, so it's going to be based on the number of empty cells. The outflow is going to depend on the number of prey. And so the situation where they're in balance will certainly depend on the prey numbers. But it also is going to depend somewhat on like how many cells there are that in the space where grass can grow. Like if it's all green, there's gonna be no inflow to grass, and prey will be drawing it down. By contrast, if there's very little grass, there's a lot competing to grow with the limited amount that prey drags it down, so the inflow will be larger. So I don't think it's specifically related to that, but the fact that you have prey at a low point is really important, for grass's ability to not be on a steep downslope. If there's lots of prey, grass will tend to go down. The outflow from grass, conceptually, we're talking, the outflow from grass will tend to be, quite large in the amount of, and likely the grass will be going down. Quite likely, unless there's a lot to still regrowing right now, but yeah.
Yeah, and I think those comments, also draw an important point that we can use stock and flow reasoning, even though this is an agent-based model, to think about how the aggregate quantities in the model relate to each other. Did that answer your question,
Yeah, it was just, yeah.
Johnny?
Yeah, I was also thinking that at that point, which is more like, say, almost 700.
Yeah.
The predator, the prey population is at its utmost lowest point.
Yeah.
So the predator does not have enough prey to feed on. So you see that at that point, the predator population also begins to sink. While it sinks, then the prey begins to rise up.
Mm-hmm.
While they rise, they have a relationship with the grass, because while they begin to rise, they feed on the grass, and that's why the grass also at that point begins to dip.
Yeah, it bears noting that there's an earlier intersection of prey and predators, where the grass is like growing really quickly, right? So it's not so much that because they're intersected, it's going to drive specific dynamics, but it's really the relative levels of each population induces basically like outflows. Predators induce outflows in prey induce outflows in grass.
So let me ask this causally, how do predators affect grass?
It's an indirect relationship.
Yes, Johnny, correct. So predators in this model don't eat grass themselves, but they eat the prey who eat the grass. So I'm going to run this model some more. I'll just zoom out here, and I'd like you to pay attention to these graphs on the right here. So we'll let it go for a couple cycles. So we observed already that this is a limit cycle similar to the stock and flow model, but with some noise for the reasons we discussed earlier. I'm going to pause it here because this is kind of an interesting topic to discuss. So this is a spatially explicit model. What do we see in this area here? What do you think is going on there? In that, so this area here, we see there's animals there. We can't at this scale see what they are, but we can zoom in. And there's a lot of green grass. There are a number of animals. Which are predators. So what do you think? How could you describe the situation in this region of the map? Yes.
They ate right in that region, so now that region, they're probably not going to be in a different region. So those predators probably going to die in that region. Ready for the next cycle. Great.
Yes. And what was your name again, please? Nicola. Thank you. That's a very good description. So in ecological terms, they would say it's the prey have been extirpated from that region of the map. So there's no prey left. They aren't extinct because they live in other regions, but the predators have eaten themselves out of house and home in that portion of the space.
You might also comment on the boundary.
The boundary of the space.
Yeah, exactly.
So we have a bounded space and nothing can go outside of it. What would happen if an animal was right in this corner? How would that affect it? Any thoughts on that? It has there's fewer other places for it to move because there's an edge effect because we're at the edge of the space.
More than that, there are fewer places predators could come to eat it.
Yes.
And fewer places that a prey could come up and eat the grass there.
Right.
Also fewer places for the prey to go if the predator comes to it.
Yes. Now we don't have a mechanism in this model for prey fleeing predators, but that would be true if we did. So I
Yeah.
see you have more to say, Professor.
Yeah,
I'm not sure.
You might want to just use this as a chance to reflect on the fact that, when we build models, digital models of systems that are spatial, it's often convenient to put them in a sort of a grid situation like this with boundaries. But you do have to sometimes consider that there may be artifacts that have been introduced. By artifacts, I mean sort of artificial phenomena that are not so much reflective of the world. There's not a lot of corners like that, in the world. The world is not a flat sheet, despite what the Flat Earth Society may say. You're not going to go to the edge and fall off, or the edge and be unable to get out. What you could do with a modest amount of extra work is have it like wrap around, for example, which would be in each direction, like a donut, right? It would be like, or a bagel, like go around this way horizontally, so the left will be connected with the right and the top to the bottom, and that would lead to fewer artificial barriers, for example. But when we look at model results, it will do well to think, to what degree is this a sort of an artificial reflection of some constraints I imposed on it for convenience in representing it? And could you do experiments that would help you understand, would those dynamics change if I relax some of those constraints?
Thanks. So those are some good points. I'll just point out if we connected the edges of the space in the way the professor suggests, like animals could go off this side and they'd reappear over here, or they could go off the bottom and they'd reappear at the top. There's some video games are like this, like I think there was one called Asteroids, where the asteroids float around in space, but if they go off one side of the screen, they come back the other side. This is called, it has a name, and it's called a toroidal space. And it's like, a toroid is like a donut, for those who don't know. And it's like you're on the inside surface of a donut. So you can walk forever and you may revisit places you've been before, but you never run into a boundary that stops you from going in any particular direction.
So it's finite but unbounded. And this is the sphere of areas of mathematics like topology, which describe these different types of connectivity of space.
Yeah, thanks. So I'd like now to draw your attention to the state space plots. So these are arranged in a third angle orthographic projection, which probably doesn't mean much to you unless you're an engineer. But this is like the top. If we imagine we had a cube, this is looking down on the top of the cube. This is looking at the front face of the cube, and this is looking at the side of the cube from at 90 degrees to the front view. So what do you think about what you see here? What do you think that tells us about the system? It's all right. It's kind of a open-ended and a tough question. But we can see predators and prey are involved in a limit cycle. Grass and predators show a similar relationship. Grass and prey, what do we see here? Yeah. Yes. So it's linear in that view, but as you point out, it's a cycle. So if we watch this as it was drawn, it's going back and forth as these go around and around. So I'm going to go now from the model to, so I said we were outputting this to a text file. And I did that with malice of forethought. Johnny, yes.
With the graph that was depicting the grass and gray.
This one?
Yeah.
Yeah,
That's-
this one?
Yes, that's the tightness of the loop as we see it. Does it tell of anything about maybe the strength and the direction of the relationship?
It does. And I think that ties into what I'm going to show next. So maybe I'll just go ahead and show that, if that's all right. So this is a manipulatable 3D version of that state space plot. So on one axis, we have predators, one is prey, and one is grass. And you can see that this whole cycle, like if we turn it this way, we see that limit cycle shape that we saw in two of those graphs. But if we rotate it over here, we can see the whole thing lies approximately in a plane. And this tells us a lot of stuff, but what the one I want to emphasize is that the intrinsic dimensionality of this system is 2 dimensions. So we have 3 state variables if we think about it in a stock and flow lens. We have grass, prey, and predators. And that's why we plotted this in a 3D cube. But the behavior of the system constrains it to a plane. It's just not one of the planes we chose to use to visualize it. It's at a diagonal to the coordinate planes. So this is important because as an agent-based model, this is actually many-dimensional system, more than 3, because we could have agent A be alive and B die, or we could have B live and A die, and propagate that geometrically through all the combinations of agents in the model. And that's how many dimensions we would have to use to perfectly describe the model. But its behavior, structure determines behavior, and its behavior is restricted to a planar manifold, it's called. And that shows a similar behavior to the 2-dimensional stock and flow predator-prey model when we look at it dead on towards that plane. I don't know, do you have anything to add to that, Professor?
Yeah, so, a key point that Wade is trying to emphasize here is the fact that this model has, if you think about it, has a giant state space. Each of the patches of grass can be in one of, is it
3
states? Each of the prey, well, it's got one state that it generates.
Yeah.
Over time. And then the predator, but a prey is either alive or dead. It can die off too, and that disappears. And then for predators also you have sort of one state, but it can die.
It's actually, there's an energy continuous variable.
Okay.
So that
Yeah.
is the second sort of state that's
variable.
going on there.
Yeah. So if you consider all the possible combinations of values that could be taken on by different prey, by different predators, whether they're alive or dead, and the amount of energy, and for every patch, how much grass it has, 3 times 3 times 3 times 3 combinations, just for the first couple cells as to the number of possible combinations of amount of grass you have. That's a massive number. But as the system evolves, it has a very high level behavior that actually can be summarized in just a few variables. It's full of sound and fury, but when it really comes down to it, it has enough regularities, all these interactions. It's the coupling, it's the interaction of predators with prey and prey with grass that mean it's not totally independent whether this cell is covered by grass or that one's covered by grass or that one's covered by grass, or the state of this prey compared to what's in those cells. Those are all coupled so much it's quite low dimensional. It's quite just a few numbers can summarize the state of the system. Essentially 2 numbers. The fact that it's 2-dimensional gives us basically virtually everything we need to know right now about how the system will evolve with just 2 numbers.
Yeah.
Not quite exactly because of stochastics and because it's not exactly 2-dimensional, but it's pretty darn close. So 2 numbers can summarize the state of this system awfully well, despite the fact there's all these different combinations at play that are so coupled that it really comes down to 2 numbers.
And those numbers are predators and prey. And we can, not exactly, but the grass mirrors the prey. So we can infer from the number of prey what is likely to be the state of the grass, whether if there's lots of prey, there's going to be less grass. if there's few prey, there's gonna be lots of grass. And then the predators lag in their peaks behind the prey. So I think I'll wrap that up. Does anyone have any final questions or comments? We've got a few minutes left.
So you should be thinking about this model sort of in your head alongside the model that we examined earlier with stock and flow. And one of the defining interests with that model is the presence of cycles, prey and predator. And that too you see coming here as a emergent behavior of a much more fine-grained description. You know, locations of predators, locations of prey, locations of grass, all these dynamics, but it still induces this high-level behavior that's very similar to what we saw with that other model. And that's something to keep in mind. Just because a lot of things are going on in the world doesn't necessarily mean you require a super detailed model to characterize it.
All right, so I think we'll wrap that up. Remember, office hours are next, and I think a couple teams will be meeting in the office hours. And anyone else who has any questions is welcome to stay for office hours.